Hello guys, it's with full joy I come your way today again. Last class on our physics, I taught you Newton's laws of motion, the first law, the second law, and the third law. And today we are proceeding the work of Sir Isaac Newton in the field of motion. We are considering conservation of linear momentum. In our previous class, I showed you that momentum is equals to impulse. And we are going to look at something totally different from what we have done in our previous class. What is the principle of conservation of linear momentum about? You know, the last law we dealt with is what? That we said for every action there is equal and opposite reaction. Now, we want to look at what is happening in a system of colliding objects. Our principle of conservation of linear momentum states that if no external force acts on a system of colliding body, the momentum before collision equals to momentum after collision. Let's take, for instance, we have an object. It collides with another object. Then this is what is happening before collision. And after collision, maybe the two of them are now moving in the same direction. What we are trying to say under this principle of conservation of linear momentum is that momentum before collision is equals to momentum after collision. We have different types of collision. Collision can be said to be elastic, or it can be said to be inelastic. If a collision is elastic, what do we mean? We mean that what? Both the momentum and kinetic energy are conserved. That is what? There is no loss of momentum and there is no loss of kinetic energy. Such a scenario of elastic collision happens within the gas molecules. When gas molecules collide together, we said they undergo what we call perfectly elastic collision. But for inelastic, another example or case study of elastic collision is your snooker balls. They can undergo elastic collision because they have a smooth body, they have smooth surface. So when there is collision, there is no loss of energy due to it. And if there is, it will be very, very minimal. It can be negligible. While inelastic collision is a collision whereby the momentum is conserved and the kinetic energy is not conserved. What do we mean by kinetic energy is not conserved? It means some of the kinetic energy during collision or during impact has been wasted, or it has been converted to other forms of energy like sound energy or heat energy. So the energy before collision will be greater than the energy after collision. In such a scenario, we said it is inelastic collision. A case study of inelastic collision is if you drop a ball to the floor and it cannot return to its initial height or to its original height, then we said that scenario is an inelastic collision. But if the ball could return back to its original height, it is elastic collision. So these are types of elastic collision. Now, for exam question's sake, there are different ways your examiners would examine you under this conservation of linear momentum. But let me try and give you some cases of collision. Let me give you some cases of collision that examiners could give you questions from. Let's go to case one. Case one. When an object collides against a stationary object. When an object collides against a stationary object, and after collision, both of them sticks together and move in a certain direction. So this is a case 1. What do we have in this case? An object is moving, collides against a stationary object. So this guy is having initial velocity, this is mass, then this guy is having mass m2, this is mass m1. Velocity here is 0 because what? It is at rest. Then the two of them collide together, they move with a common velocity. For you to be able to address these questions politely, don't forget this, your Cartesian coordinate. If this is your y-axis, this axis is positive, then this axis is negative. This axis is positive, this axis is negative. So please, for this case, any movement towards your right, you call it positive. And any movement towards your left, you call it negative. So let's look at it. Momentum is what? Mass times velocity plus mass. I've told you that the velocity here is what? Is 0. Equals momentum before collision equals to momentum after collision. M1 plus M2. Two of them stick together. This is their common velocity after collision. So for this particular scenario, we can now say M1 U, and let's call this U1 equals, this is 0, M1 plus M2 equals V. You cannot use this formula for every scenario. Let's look at another case, case 2. Let's consider an object that collides against another object, a stationary object, and two of them, after collision, one returns back to where it is coming from, and the other moves in this direction. Let me take it again. An object collides against a stationary object before collision, and after collision, it moves back, it changes in direction, and the other object moves in the direction of the initial object. So let's call this one M1, U1, M2, U2 is 0, M1, V1, M2, and V2. So momentum before collision equals momentum after collision. We have M1, U1 plus M2, 0 equals M1, V1. Don't forget, this guy has changed direction. Then it's going to be what? Negative minus plus M2 V2. What's the direction of this? It's like this. It's going to be what? Positive. So you can now modify your equation to become M1 U1 equals minus M1 V1 plus M2 V2. So you just need to understand the concept we are using to know if it is positive or negative, to differentiate between your initial velocity and final velocity. Let's look at another case. Case 3. When your object is colliding against another object that they are moving in the same direction. They are moving in the same direction. For such a case like this to occur, it means this guy is moving with a velocity that is higher than this guy's velocity. So after collision, let's say they collide. What should we create now? Okay, they still continue in the same direction after collision. After collision, let's say after collision they stick together. Let's use this. They stick together and they move in the same direction. So what are we going to have? You have your M1 U1 plus M2 U2 equals M1 plus M2. Why do we say this? Because the two objects collide together with a common velocity. So this is the equation for this scenario. Let's just get one more scenario and we go ahead to solve questions. Let's consider objects collide and they are moving in opposite direction before collision, and after collision they also move in opposite direction. They collide against themselves and they bounces back. So let's look at what is happening. M1, U1, M2, U2, M1, V1, M2, V2. So we have our M1, U1, and this is moving in that direction. That's minus M2, U2, equals which direction is this facing? Negative direction, M1, V1, and this is facing like this, M2, V2. This is the equation you are going to use to solve such a question. Then the next thing you need to know is what is happening when an object is moving inside a lift. That is another application of your Newton's law of motion. So let's consider another application of Newton's law of motion, and that is weight of objects in lift. If your weight is 80 Newton, you enter a lift and the lift is moving up. Your weight is not going to be 80 Newton again. Your weight will be a function of the acceleration with which the lift is moving up. We call it an apparent weight. If the lift is coming downward, your weight is also going to be different from when the lift is moving up. So how do we know the weight of objects inside a lift? Let me quickly sweep you through that. Let's say this is a lift, and this is Mr. Koi inside the lift. Your lift is suspended with a cable. The cable will have a certain tension. The weight of this guy on ground, let's call it W. So for the first case, when the lift is moving upward, what do we have? We said the lift is going like this. You have your resultant force, Fr. So when we have two forces in different directions, your resultant force will be T minus W. Why do we say T minus W and not W minus T? It's because the lift is moving upward, which means your tension is greater than the weight. So we have T minus W. Your Fr is given by Ma. Your tension in the string is the apparent weight of the object inside the lift. And your W is mg, which is the real weight of the object on ground. So make our T the subject of the formula. We have Ma equals, that's plus mg. So your T is what? Apparent weight. Apparent weight of the object when the lift is moving up. Now, what happens when the lift is moving down? B. When the lift is moving down, what happened there? Take your lift as usual. This is Mr. Koi inside the lift. This is the weight of Mr. Koi. This is the tension of the lift. The lift is moving down. That's your resultant force. Your Fr will now be W minus T. I told you that you first take the direction of the motion first. W minus T. Your Fr is Ma. Your W is mg. Your T is the apparent weight of the object inside the lift. Make your T the subject of the formula. You have it to be mg minus ma. So your T equals to m bracket g minus a. So this is the formula of the weight of an object inside the lift when the lift is going down. Now let's look at another scenario when the lift is stationary. When the lift is stationary, what is happening? It means acceleration equals to 0. So if the acceleration equals to 0, just say T equals to mg plus ma. Therefore, this guy equals to 0, mg plus 0. Your weight inside the lift equals to the weight of the object on ground. Take note of that. Another scenario where T equals to mg is when the lift is moving with uniform velocity. When the lift is moving with uniform velocity, don't forget the point I gave you under linear motion. That when an object is moving with uniform velocity, there's not going to be acceleration. Why? Velocity is not changing. What is acceleration? Acceleration is what? Change in velocity with respect to time. So when your velocity is uniform, steady, or constant, acceleration is going to be zero. So when your lift is either moving upward or moving downward with uniform velocity or steady velocity or constant velocity, don't forget acceleration is going to be zero. Therefore, the weight of the object in the lift will equal to the weight of the object on ground. And lastly, let's assume the cable of your lift break and the lift is falling freely. When lift is falling freely, you understand me? The object inside the lift will experience weightlessness. Weightlessness. What does that mean? It means the weight of the object in the lift is going to be zero. Is going to be zero. That is when the cable break and it is falling freely. The weight inside the lift, the object inside the lift is going to be weightless. So I believe you understand this concept of conservation of linear momentum. So let's take our three worked examples. Then you have your practice question as usual. So our normal approach of solving question, you read it, you reason it, you record it, you relate it, then you do what? You result it. So let's read our question. A ball of mass 0.5 kilogram moving at velocity 10 meters per second collides with another ball of equal mass at rest. So M1 equals M2. And they said the other one is at rest. So that is to say your U2 equals to 0. If the two balls move together after impact, what is their common velocity? So let's reason this question and relate it with diagram. A ball of mass 5 years, mass here is 0.5 kilogram, is moving with a velocity 10 meters per second, collides with another ball at rest. Then what happens after collision? They stick together. And they are now moving what? They move together. So, which formula are we going to use? You don't need to memorize those formulas. You can always create your formula. M1, U1 plus M2, U2, that is 0, equals M1 plus M2, bracket V, which is the common velocity. So what's your M1? 0.5. What's your U1? 10. And this guy is 0, equals M1, that's 0.5. They've told you equal mass. M1 equals to M2 plus 0.5. At the common velocity we are looking for. This plus this gives us 1.0 V. This times this gives us what? 5. So your V equals to 5 divided by 1.0. So common velocity after impact equals to 5 meters per second. So the second question, let's look at the second question. An object of mass, permit me to clean this up. So an object of mass 2 kilogram is moving with a velocity. What is the velocity? 3 meters per second. Collides head-on with an object B. So they said an object A, so let's call it NAUA. The MB, mass of MB is what? 1 kilogram. Moving with velocity B, VB, UB, that's 4 meters per second. They said in opposite direction. After collision, both stick together and move with a common velocity. So this is how we are going to have it. It collides with another ball moving in opposite direction. This is your object A, and that's your ball B. Your velocity here is 3 meters per second, and your velocity here is 4 meters per second. The mass of this guy is 3 kilograms. The mass of this guy is 1 kilogram. And what happens after collision? They said after collision, both stick together so that they move with common velocity. So this is your A plus B now moving. Now, the question now is this. Yeah, this is the technicality of this question. Which direction will they move? Are they going to move like this after collision? Or they are going to move like this after collision? This is the logic. They move in the direction of the one with higher momentum. What is the momentum of this guy? That's 3 times 3. That's what? 9. What is the momentum of this guy? 4 times 1. That's what? 4. It means the momentum of this one is higher than this. They continue like this. So after collision, they move like this. So once you've been able to do that, you don't have problem. So let's follow our normal MAUA plus. Is this my plus now? This will be minus MBUB equals MA plus MB bracket the common velocity. So let's substitute. We have 3 times 3 minus 4 times 1. So equals 3 plus 1 bracket 4. This 9 minus 4 equals to 4V. 9 minus 4 gives us 5 equals to 4V. So your V will now equals to 5 divided by 4 meters per second. That is the common velocity they have after collision. Don't forget how we're able to know the direction after collision. Because in the question, they did not tell us the direction after collision. Just look at your momentum. Which of them has the higher momentum? So the final direction will be in the direction of the one with higher momentum. This guy will push this guy, and they continue like this. And the last question for today, is on object inside a lift. So just a girl of mass of the girl is 5 kilograms, stands on a spring-weighing machine inside the lift. If its acceleration of the lift, the acceleration of the lift is 2 meters per second square, what will be the reading of the machine? That is, what will be the apparent weight of the girl when the lift is moving upward? What is the formula? The formula is M equals what? A plus G. So your apparent weight, that's 55. That's A is what? 2 plus 10. That's acceleration due to gravity is constant. That's 55 times 12. You get your answer in Newton. That is the weight when the lift is going up. Then when the lift is coming down, we have gotten the formula to be mg minus A. That's T equals what's your 55. What is your G? 10. And what is your A? 2 meters per second. So you have 55 times 8. You get your answer in Newton. And lastly, when it moves with constant velocity, C. At constant velocity, I have explained, at constant velocity, what happens to acceleration? Acceleration equals to 0. Therefore, your T equals to what? Mg. So T equals to what was your M? 55 times 10. That's your 550 Newton. So I believe these are crystal clear. Please attend the practice question in the comment section. If you have any problem you couldn't get, please send them to us through the comment section. I'm going to attend to them. And don't forget, share this video with your friends, comment, and subscribe to our channel. See you in the next class.